We are going to look at the surface charge density in this video on a conductor that's kept in an external field, and then calculate charge density on the surface generated or induced as a result in two scenarios. And so let's start working on the concept. The idea is based on the matching conditions that we have learned in the past. And so you have again the charge density on the surface, sigma rs. Our goal eventually is to find out what this is, and then you have the electric field outside the conductor, and then we know already that there is no electric field inside the conductor due to the induced or the electrostatic induction effect. And so the component of the electric field that is along the normal is discontinuous, with a discontinuity that is given by the surface charge, and the component that is along the plane or parallel to the surface is continuous, because the other side is 0. Now, given that the electric field inside the conductor is 0, we can get the electric field just outside the conductor. The component of it is along the plane of the conductor is 0, and the electric field outside would be along the normal, and it is given by sigma rs over epsilon 0. So this is essentially definition of the conductor, that the electric field just outside the conductor is strictly normal to the conductor surface, and is proportional to the local surface charge density. And experimentally, if you measure the external electric field, then you can determine the surface charge density. Remember, measuring electric fields is easier, not so much the surface charge densities. And so you can actually calculate the surface charge density when you know what the electric field is just outside. So we're going to now take a look at a couple of applications of this formula. First one, of course, is something we have looked at in a slightly different language in example 5.1. So first application is surface charge density on a polarized sphere. Right now the sphere is polarized because it is kept in an external uniform potential. And so for this we need to calculate E out basically, and that is going to be uh, composed of two components. So you just do negative epsilon 0 partial derivative with respect to r, because it's radially outward, the electric field is along the radial direction, so we can calculate the potential which has two components: the external potential er cosine theta, which is basically Ez, and that's the potential, and you take its derivative along the normal direction to get the electric field component. And then there is the self field component, which we have calculated in example 5.1. So we combine these two, take the derivative with respect to r at r equal to r. So these are to be substituted r equal to r, when you do the calculation, which is pretty straightforward, you get 3 epsilon 0 e cosine theta. That is the total charge density, and you can easily see that this is non-uniform charge density. That's why it's also very difficult to calculate this. It's not, you need to do a lot of work to be able to do this calculation. One other thing to note here is that when you do when you take this charge density and use that to calculate the dipole moment, because that is another very interesting and useful quantity for a polarized sphere, you want to be able to calculate its total dipole moment. You can see, because sigma theta has a derivative, is only theta dependent, or rather it is only dependent on electric field that is in the z direction. The component of r here that is going to give us non-zero contribution is going to be only along z direction. So let's first write down the r vector, which is r sine theta cosine phi along the x direction. The y component is r sine theta sine phi along the y direction plus r cosine theta c hat, and the angular integration, which involves the integral over the angle theta, only survives in the case of the z component. The other two components do not contribute. So you get d theta sine theta cosine theta sigma theta along the z direction, which then is a very simple integral to do. You can get 4 pi epsilon 0 r cubed e into the z direction. And this answer that we got for the dipole moment with a slightly different way of calculating the charge density actually matches with the calculation that we did in example 5.1. Let us now give you one more example without doing the calculation. Is the case of a conducting disk of radius r. So here's another example or application rather. Where we have a conducting disk of radius r, and has a net charge Q. And so the application 5.1 in the textbook actually does this calculation. It is pretty involved. We are not going to go through it. I will just give you a brief summary of what that amounts to. Is this is how it goes. So to calculate the charge density on the surface of a disk, it's a non-trivial sort of problem. There is no simple way to do that, and the way it is done usually is to take advantage of equipotential lines due to the potential of a line segment of a finite length, let's say situated from minus L to plus L. So it's a line segment of length 2L, and then it is going to have Pauli ellipsoidal symmetry surrounding that line, and then we can calculate the charge density on any surface for a given value of the potential on that ellipsoidal surface, and then you squash that ellipsoidal surface to calculate the potential due to a disk, which then you can translate into the charge density by taking the appropriate derivative of that potential. So it's a multi-step calculation, if you will, and when one does that, we get after the squashing procedure, we get the charge density on a disk of radius r as r squared q over 4 pi r inside the square root r squared minus rho squared, and rho is the standard cylindrical radial coordinate. Okay, so that completes that discussion of the use of matching conditions to determine surface charge density on a given surface. And it's not always trivial to find this charge density. Finding electric fields, experimentally you can measure them, if you will, and so you want to be able to calculate these charge densities based on the measured results. Another property of the electric conductors is their screening and shielding properties, which what we will look at in the next video.